Good morning and welcome to the second webinar with Swegon Air Academy and the Swedish Association for HVAC Engineers. My name is Veronica Eid. I'm the Secretary General of the Swedish Association Swedvac.
And my name is Lydia Karlefors and I'm here for Swegon Air Academy.
This is the second webinar. For those of you who followed the first one, we had focus on school children and schoolwork and their performance when they had a bad or better indoor air quality, excuse me. This seminar will have another focus and we will have a presentation from Lydia.
Our speaker today is originally from the UK, but has worked in Sweden for 30 years before returning to the UK 20 years ago. He has worked in 4 continents all over the world and studied the impact of indoor environment on people's behavior in both cars, buses, trucks, even airplanes, but mainly in buildings. I'm very proud to present today to you David Peter Wyon.
And for those of you who are with us online, don't forget that you have a chat function in the Bambuser that you can use to speak to Professor Wyon at the end of the webinar. Thank you.
Good morning, good afternoon, good evening. Some of you are in different time zones, and I'm very pleased that you have taken the trouble to plug in for this presentation. We didn't make such an impact online last time because webinar is a rather new format for us. Today I'm going to talk about my experiments and one or two other experiments which have shown how temperature and indoor air quality affect adults when they are trying to work. And the title of my presentation is Thermal and Air Quality Effects on the Performance of Office Work. I'm associated still with the International Centre for Indoor Environment and Energy at the Danish Technical University. And this is part of Swegon Air Academy's series of lectures from researchers in Scandinavia. The centre where I work was established in 1998 at the Technical University of Denmark, originally in the Department of Mechanical Engineering, because it was seen as dealing with ventilation. Today it's in the Department of Civil Engineering because it concerns all aspects of building. We have 7 climate chambers, quite large ones, and 5 test rooms where we can create realistic conditions in the building behind our office block in the Danish Technical University. And we have done a wide range of studies which are aimed at seeing how people react. What do we get for the money we spend on improving the indoor environment? It's interdisciplinary research. We have sometimes medical doctors working with us, psychologists, behavioral scientists, but mainly, of course, engineers and architects who are the ones who design and control and maintain our buildings. That's a view of our engine room below the climate chambers. It's quite a big undertaking to run so many climate chambers independently. Our approach is to perform experimental studies of human subjects who are exposed to indoor environmental factors, either in climate chamber experiments or in more realistic conditions. Halfway between the laboratory and the field are what we call field laboratories. These are simulated environments which are as close to the real environment as possible. For example, they have view out from windows, which is rare in climate chambers. And then we do field intervention experiments, not field surveys. And I want to emphasize the difference between surveys, which ask people how they are, how they feel, how they think they're working, and experiments in which we change something in their environment. We do this in as covert a way as possible. Of course, it's not always possible to keep it from subjects what we have changed. If it's noise, for example, they hear it. If it's temperature, they feel it. But air quality is one of those which is easy to change without their knowledge. They have no way of telling whether we are giving them 5 or 50 liters per second per person. And that is true in the climate chamber, but also in the field. So we're very happy to do work of that kind because we can then rule out the causal link that goes via awareness. In other words, you can criticize many experiments from the point of view that people know what they're experiencing and they have an expectation of how they will react. We try to eliminate that as much as possible. I'm going to talk to you first about a series of experiments on air quality, how it affects health, comfort, and productivity. We performed a series of laboratory simulation experiments in one of these field laboratories with windows, with office chairs, and the normal kind of layout. We used only 30 subjects in 5 groups. They worked for 3 to 5 hours, which is about as long as people work without a break. You can reset your attention by going for coffee or by having lunch or going to a meeting, and then work differently, better when you come back. But if you're working continuously for 5 hours, then fatigue sets in. And you become more sensitive to the effects of the environment. We think 5-hour experiments are long enough to show these effects. We use a repeated measures design. If we didn't, then we would need many more subjects. If we were using an independent measures design where we randomize people into different conditions, we would probably have to have over 100 subjects in order to get the same sensitivity. But by removing the source of variance, that is the difference between people, using each subject as their own control, we can manage with far fewer subjects. So each subject experiences each condition, and we compare their responses, how they feel, what they say about the environment, how their symptoms have become after being exposed to these different conditions with themselves under other control conditions. And we, of course, balance the order of exposure to conditions, because if they experience condition A first and condition B second, then we would be confounding the effect of sequence with the effect of the difference between A and B. They performed simulated office work, as realistic work as possible. I want to emphasize this. It was not psychological tests designed to be sensitive to some aspect of the environment. They did what you do in your office. We'll be looking at the different aspects in a moment. We asked them about their sick building syndrome symptoms of the eyes, nose, throat, and so on, and the more general symptoms such as headaches and difficulty in concentrating, using what are called visual analog scales, and I'll be showing you some of those in a moment. We derived the perceived air quality, and that is based on a subjective response telling us how acceptable they feel the air quality is. And this was assessed both by occupants and by visitors. The perceived air quality is based on the DTU scale of acceptability. You'll see that to the left on your screen. It runs from clearly not acceptable at the bottom to clearly acceptable at the top. In the middle, there's a gap, so you're not allowed to sit on the fence and say, so-so. It's not bad, not good. You have to decide when marking the scale, as you can see somebody's doing here, by putting a transverse mark, whether it's acceptable or not. In other words, the upper part or the lower part. The lower part of the lower end of the upper part is called just acceptable, and then it takes on again from just not acceptable. And that forces them to choose. So we get a binary response, acceptable or not, and we can relate that to where on the scale they have marked. We get much more information this way, because if we just said yes, no, then we get one bit of information. But when they mark a visual analog scale like this, we can measure where the mark is in millimeters, and that gives us much more information. Is it clearly acceptable or just acceptable or somewhere in between? And we have done this so often that we have a relationship between the acceptability marking, where it is on average, and the percent who would be dissatisfied. On the right-hand side of the scale, you can see another set of visual analog scales. Don't worry if you can't read them, but they are partly to do with direct symptoms, such as your nose is easy to breathe through or clear, or it's blocked. And specific things like symptoms such as eyes sore or not sore. And further down, we have symptoms, more general symptoms such as fatigue, headache, and difficulty in concentrating. And these are not measurements, except that we measure their response in millimeters on a scale. But they are a response. It's behavior. And they are not normally distributed normally. For example, if you have a headache, you may have a severe headache or you may have no headache. But we want to know where you are on the scale, but it's not normally distributed. Most people, fortunately, have no headache. So on the frequency diagram, we have a lot of people with no headache, very few unfortunate people out here with a severe headache, and in between something like this. It's called a J distribution statistically, and of course you can't use normal statistics based on the normal distribution. So we use non-parametric statistics which do not make that assumption in order to analyze whether the way those scales were marked under condition A differ from the way they were marked under condition B. We are interested in whether there was a significant difference and in what direction it was, but the size of the difference is of course not of particular interest. Our main focus is on the performance of typical office tasks because it's difficult to quantify symptoms in money. And money is required in order to improve the indoor environment. It costs money to build a better place. It costs money to bring in more outside air and to control the temperature more exactly. And that money has to come from somewhere. And if we can show, as we have over and over again, that people work less well in poor environments, then the money comes from the improvement in productivity. In fact, since providing a good indoor environment usually costs about 1% of wage costs of having people actually present doing work, then a 1% improvement in productivity would pay for doubling the budget for providing a good indoor environment. As engineers, we see that. Economists take some convincing. Therefore, we have to do good experiments in order to show them just how much better people will work if they are given good air quality, good temperature control, good lighting, absence of noise, view out, and so on. And I shall be showing you how people react to all of these factors in the course of this lecture. We normally use a set of simulated office work tasks. They go from word processing, that is typing, a text into a computer where we can measure the speed with which they do this and the number of errors they make. They choose their speed of working. It's not imposed upon them, as it is in some tests. There's often a trade-off. As it becomes more and more difficult to work, you can choose to maintain a constant error percentage of, say, 5% or 2%, depending on how pedantic you are and how much you dislike proofreading, and slow down in order to be able to maintain this error percentage. Or you can maintain your normal speed and accept that you're going to make more errors. Jumping ahead, we find that almost everybody chooses to maintain an acceptable level of errors and slows down. So poor indoor environmental conditions translate not into more errors, but into slower working. And that's a personal choice made by our subjects. And we believe, since we've observed that in real life too, that is what happens in real offices. After typing, you have to proofread. That's one of our activities. We have texts in which there are inserted errors, which have to be found and underlined or ringed. And again, we can measure how much text they manage to proofread in a given time and how many errors they miss, or how many errors they make, where they underline something that is in fact correct. The errors can be of many different types. They can be spelling errors, they can be grammatical errors, they can be errors of content. And it takes quite a lot of concentration to do good proofreading, as I'm sure all of you know. Point is, it's something we do every day in our normal work. Whatever work we do, we eventually have to write something and proofread it. Sometimes people have to think more logically, symbolically. Mathematics is a good example of that. We have tests of addition and multiplication, and we have also, not always, but from time to time, used tests of creative thinking. That I've done 6 experiments showing how the indoor environment affects creative thinking, but since that is not one of the aspects that I'm going to deal with today, I won't go into how those tests work. But it is possible to measure how well people think creatively. In other words, where there is no defined correct answer, as there is in all the previous ones, mathematics, you either get it right or you don't. In creative thinking, we ask them to come up with new ideas, and there are any number of good ideas. Well, how do you score that? Well, I developed a method based on information theory, which simply assigns a score depending on how many other people thought of that idea. So if you get, if you give an answer that everybody gives, it's a very low score. If you are the only one who came up with it, you get the maximum score, and so on. And I don't even assign the numerical value. It's assigned by information theory. But again, as I say, that will possibly become another lecture because there's a lot of data on creative thinking. There are many pollution sources indoors, from which the chemicals that that cause us to say the air is poor or stuffy, or which affect our ability to think, are coming. They come from the people we share the room with, from ourselves, from our clothing. They come from the books and papers that we always have in offices. They come from the electronics that we have with us in offices, the machinery, copiers, printers, and so on. And they come from the furniture, then the walls and the floor. And we have also indicated that there are pollution sources in the supply system for the air. That's not clean air that comes in there. It was clean before it was taken into the processing, but there's usually a filter there. The purpose of a filter from the point of view of an engineer is to keep his equipment clean. But I've always told people that if you want to breathe clean air, you don't put your face into a vacuum cleaner bag, because that's where the dust is. And yet, all the air that we are breathing indoors has come through such a bag that collects dust. And it does amount to a fair source of pollution. And therefore, you get something for changing the filter. You get cleaner air. And in this series of experiments, we evaluated how much that means for office work. In this field laboratory, we had a screen across about a quarter of the floor area, and behind that we could insert various sources of pollution. And a typical control day, there would be nothing behind the screen, but a certain amount, 10 liters per second per person, of fresh air coming in directly through the wall. It hasn't even been through a filter or through the building's ventilation system, so we know it's clean. On other days, there would be office items behind the screen. The most usual item is an old carpet that has absorbed all of the chemicals that were in an office for a dozen years. And we hang that up in strips. The area of the carpet corresponds to the floor area of the room, and the air that's coming in passes over this carpet before being circulated to the people who are breathing it. And that makes a noticeable difference to the quality of the air. And the experiment was designed to find out how much air they need to counteract that, and how it affects their work. 10 liters per second per person coming in both cases, and either with or without carpet behind the screen. The subjects have no way of telling, apart from sniffing the air, well, what is behind the screen. They're not allowed to look over it or round it or under it or anything like that. And they're, of course, not informed of what's behind the screen. This is an experiment that could be done in the field. This is, in fact, one of our offices next to our own offices. So it's built exactly as a normal office is, with, in this case, low-emitting materials. We also did an experiment with the source always present, and then we compared 3 liters per second per person with 10 with 30. In other words, tripling the air supply rate and multiplying it by 10 to see if that helped in a normal office. Biofluents are always present, and a 20-year-old carpet from an office building. And the first experiment was replicated in Sweden, so independently of ourselves. So we are fairly sure that you would get this result if you did this experiment in your own offices. The perceived air quality, as reported by visitors, quantified in terms of our estimate of how many people would have given thumbs down, in other words, reported that they were dissatisfied with the air, marked the scale on the lower half, was like this. With the source present, about 20% dissatisfied. That's not unusual. That's not a exaggeratedly bad environment. 20% dissatisfied represents 80% satisfied, which is ASHRAE's definition of a comfort zone, where 80% are satisfied. With the source absent, we could get that down to about 15, as you see in the left-hand columns. By increasing the airflow rate from 3 to 10 to 30, we have a dramatic improvement. With only 3 liters per second, nearly 40% were dissatisfied. Remember, in the left-hand part, there was 10 liters per second. For some reason, more were dissatisfied with the 10 liters per second, perhaps something to do with the balanced design, where they had experienced both 3 and 30. They had a yardstick. And with 30, we're down to about 15 again, dissatisfied. Not 100% satisfied, but considerable improvement, and of course, highly statistically significant. Their SBS symptoms were also affected by these changes in their environment. Headache was significantly reduced when we removed the carpet from behind the screen. Difficulty in concentrating, highly significantly reduced when the source was absent. The p-value represents the possibility that these observed results could have occurred by chance. In other words, they couldn't. This is a very high level of statistical significance and very rare in behavioral studies. Difficulty in thinking clearly was also significantly affected by an increase in the ventilation rate. And here we're getting much closer to something for money. People come to work to think clearly. They can't do that if they're having difficulty concentrating. They can't do it if they have a headache. So we believe that even these results would be a strong argument for improving the quality of air in offices. But we went further, and the performance expressed as a relative performance, a percentage change, or a proportional change, percentage change in this case, was significantly affected by the changes with the source absent, source present, and with the source present the whole time by increasing the ventilation rate. So you can see we're talking about a 4-5% improvement in performance, and that would pay for improving the environment many times over, as I already mentioned. This is another experiment in the series where the source of pollution was electronics. At that time, people were using what I believe today are called fat boy monitors. That is the big kind of CRT monitors. And they have a lot of electronics that gets quite hot. And a lot of air goes through the casing. That's why it has gaps in it. They often have a fan even to push in air and blow it out again in your face. And we believed that this was causing pollution. But it's only when they're new. So the subjects worked on old PCs so that they were in the control condition, not subject to electronic pollution. And behind the screen, we had new ones, heated up for in the first months of use. And the subjects didn't know if they were present. So the control condition was like this, with nothing behind the screen and old computers to work on. And then in the next, or the other condition, we brought in 6 old computers and ran them behind the screen. And these had been run for less than 500 hours, while the ones they were working on were more than 3 years old and had stopped emitting as much pollution. This is what it looked like from, if you were able to climb up near the ceiling, you would be able to see over our screen, and you can see the 6 monitors behind. It's difficult to remember that that's what offices looked like in those days when we did this experiment. This is done in the late 90s, and it was one of the first times that an effect of air quality on office work had ever been shown. Since then, it's been shown by many people all over the world. Perceived air quality, again in terms of percent dissatisfied, was significantly affected at the P less than 0.01 level. With the PCs absent, they were only 10% dissatisfied with the air quality, whereas as many as 40% were dissatisfied when we were running computers behind the screen. That previous one was by visitors, people coming in from outside, and they're notoriously more sensitive to the environment. They haven't been in it for as long, so it meets them in the doorway. And of course, bioeffluents play a part in this too. The occupants got more used to it, but still, with when they rated the air freshness on a scale of 0 to 100, then there was a significant difference in how they rated the freshness of the air on one of those visual analog scales. Performance, text typing, word processing, if you like, was significantly affected by the presence of the PCs. They worked less well when the PCs were running behind the screen. Now, was that heated plastic or was it heated electronics? We did a supplementary experiment to show that. And on the left, you see the whole PC. On the second, we'd taken the casing away, and it was only the electronics. And the third staple from the left shows just heating the casing. And that was no more than the background. So it wasn't the casing, it was the electronics. We think it's the flame retardants that are on new electronics that when heated, give off a lot of unpleasant chemicals that reduce the quality of the air. This is an experiment we thought would lead to a new industry of point exhaust from the casings of electronics. I still think that would be a good idea for printers and for copiers, because they still give off a lot of pollution. But nowadays we work on flat screens, and it turns out that they do not provide that amount of pollution, but other electronics do. If we express our results in the red circles of relative performance as a function of liters per second per olf, and that is person equivalent. In other words, we have also quantified the carpet in terms of equivalent number of people. That's a somewhat controversial way of dealing with all the different pollutants, but it works from an engineering point of view in terms of how much fresh air we need to bring in for each olf in the source strength. We see that we have a typical curve like this, where the first improvement from 1 to 2 to 3 has an enormous effect in performance, and it then doesn't level off entirely, but you continue to get improvement up to at least 10 liters per second. If we express, and this is perhaps interesting for people who run buildings rather than design them, if you express relative performance as a function of the percent dissatisfied with the air quality, and that is an empirical quantity you can discover by going around asking 100 people, or dealing out questionnaires electronically or as pieces of paper, and find out how many people are satisfied or dissatisfied, or even better, using the DTU scale of acceptability. You can use this relationship to work out what a percentage of decrease in performance you would get as you get up towards the 50, 60, 70% dissatisfied with air quality. So you can turn data quality quantified only in terms of people's subjective responses into an estimate of performance, and that can be turned in its turn into can be recalculated in dollars for a particular workplace. The air that we bring in the field laboratory, or in this lecture theatre, or in your office, mixes with the other air in the room. There are various ways of getting it to the breathing zone slightly more efficiently, for example by displacement ventilation, where the air comes in low down and it comes up with your self-convective current and reaches your nose in slightly better shape than if it had been pre-mixed with all of the air in the room and with emissions from other people. But the best we can do is, short of giving people a mask to breathe, as fighter pilots have, is to bring the air all the way to their desk and allow them to breathe it exactly as they would in their car, with a vent which they can position where they like. And here's a very early, rather crude example of a personalized ventilation system. which delivers supply air more efficiently directly to the breathing zone. And my colleague Arsen Melikov is a pioneer in this area and has developed many better ways than this of delivering air directly to the breathing zone. But all I'm going to say today is that in an experiment that he ran, sick building syndrome symptom intensity was reduced by providing personalized air as opposed to not providing it, providing the same air, but through the normal ventilation system. The subjects were able to adjust the flow rate and position individually, and of course that greatly increases the between-subject variance, so it makes it even more difficult to show effects on performance, because there are other sources of variance. It doesn't mean the effect is less, it just means that the variance is greater, so it's more difficult to show an effect because of the variance between people. But even with that disadvantage, by allowing them to adjust it themselves, perceived air quality and the performance of office work was significantly improved in a 26-degree office with 20-degree supply air to such a PV system. However, this must be regarded as an effect of both temperature and indoor air quality, because they were able to cool themselves with this blower as well as provide better air. So it's not an effect of indoor air quality alone, but it does show an advantage of the PV system for performance. Well, people say, who don't want to spend the money on bringing in more air, they say, well, all that's very well. It's done in a laboratory. These are subjects who know they're taking part in an experiment. They're paid to take part in an experiment. It wouldn't work in practice, and that's where we are having to pay to bring in more air. So we took the consequences of this criticism. It's a fair criticism of our work. And we did the same experiments or similar experiments in the field. This is a picture of the actual call center where the experiment was done. It was a directory inquiries call center where each operator, there were 24 of them at different workstations, were working with an intelligent search system with a computer under time pressure, and time pressure that you can't imagine. Each one of those was expected to deal with 400 calls an hour, not per day, 400 calls an hour, in which they had to find out what the caller wanted and deliver it to them as quickly as possible. A measure of their ability to do that was how long it took them before they could say thank you and goodbye and go on to the next caller in the stack of calls waiting for them and exerting time pressure upon them. This really is hard work. It's not like you or I who can take a break or flick to a CNN or something if we find we're not concentrating very well and then go back to work. They have to keep taking calls and their work is monitored. It was because their work is so well monitored that we knew, both online and offline, exactly how many milliseconds they'd used for each call. And that is data we can use in an experiment, and that's why we chose this call center. It is on the top floor of an office building in a rural part of Denmark, not far from Copenhagen. A very nice working environment with enormous, wide views out from every workstation and well designed, well ventilated. And our experiment was designed as a 2x2 design with either a new or used filter and with low or high outdoor air supply rate. The beauty of this is that it was a blind experiment. The subjects had no way of knowing if we had changed the filter that day or that week. And they had no way of knowing if we were giving them a lot of fresh air or a little. They couldn't even tell by seeing how much air was coming in, because it was always the same amount of air. What we did was mix in a little or a lot of fresh air into the recirculated air that was coming in, reject more or less of the exhaust air. So from a behavioral point of view, this is the perfect experiment. People are in their normal working environment, they're doing their normal work, it's real work for which they're paid, it's difficult work, it's hard work, and they are completely unaware of the conditions that we've made for them. You say, well, why didn't we change the temperature? Well, we did try to do that a little, and people were knocking on the plant room door immediately. The moment we changed the temperature, even by half a degree, they complained. because they were very sensitive to temperature. So this is not a thermal experiment. We gave them the temperatures they were used to and which they demanded, and all we did was change the air quality. Each intervention lasted a week and was repeated once. We changed the outdoor air supply rate by changing the dampers in the existing system from 34 litres per second to 344 litres per second total. And that is from 8% to 80% of the total flow rate of 430 litres per second into that room. That ventilation rate corresponds to 3.5 air changes per hour. That is 7 times what you get in a building, a dwelling that is built according to the most countries' norms. So it was well ventilated. And we gave them 8% fresh air or 80% fresh air. And that corresponds to going from 2.5 litres per second per person to 25. 10 times improvement in the proportion of fresh air. And we changed the filter. You can see its position in the system. It filters both the incoming air from outside and the return air taken from the exhaust vents. And we either had a new filter or a 6-month-old used filter loaded with dust. And it was the same dust because it had been used in that office. So nothing unusual about the conditions, it's just different phases of the filter changing cycle. Average talk time with a new filter in place was significantly, or almost significantly changed when we gave them 25 litres per second instead of 2.5. P less than 0.06 is borderline significant. It was a 6% decrease in the talk time, the time it took to answer callers' questions. The average talk time with a high outdoor air supply rate was decreased by 9% when we put a new filter in place compared to the old filter. But when we changed the supply rate with a used filter in place, giving them more air through it actually made things worse. Their talk time was 8% higher with more air going through it. And how can that be? The size of the effect on performance was 6 to 9%, was similar in both field and laboratory experiments. Increasing the outdoor air supply rate had positive effects when the filter was clean, but providing more outside air through a used filter had negative effects. And we think that's because a filter contains a huge surface area of dust. Charlie Weschler has calculated that a full filter, just before it's changed, has a dust surface area corresponding to the whole floor area, the whole ceiling area, plus all of the walls. It's as if you walked into a room entirely covered in dust. You've probably never seen such a room. You wouldn't want to be there if there was such a room. And yet, the air we breathe has been passing over an area of dust that large. I've always said that it's better to breathe air before it goes into the vacuum cleaner than after it's been through the vacuum cleaner. And you should try it one day. When the air has been passed through the dust collected in your house, it's not very nice to breathe. In fact, you may get a coughing fit from breathing it. And this is what happened here. We believe that the negative effect of passing more outside air through the dust was that the substances on the dust, this is just speculation, were more easily able to evaporate when air with a lower partial pressure was passed over them. So it was transporting more pollutants which had accumulated over the years, or over the months that the filter had been in use, transporting more of those back into the office all at once. This is a slide I shall show 3 times. I have addressed only the first bullet point, and its conclusions from this lecture, which I hope you'll share when you've listened to me for an hour. The first conclusion is that office work is performed more slowly in poor air quality. Shall we say CO2 levels above 900 ppm in a typical office. The other conclusions we'll be looking at the evidence for, and I shall show them in bold as I believe I've justified them. I now move on to a second series of experiments that was paid for by ASHRAE in this case. It was known as Research Project 1160, and it was to determine limiting criteria for human exposure to low winter humidity indoors. That's a problem that we share with Canada and Russia, and quite a number of northern states in the United States. And I'm sure parts of China have low winter humidity, even though we think the China we visit has high humidity. There are cold areas of China too, and of Northern Ireland of Japan. It can be very dry indoors in the winter. This was published in the HVAC&R Research Journal, which is ASHRAE's archival journal, in 2006. And I was one of the project leaders in this series of experiments. We took 60 subjects, both male and female, including normal, sensitive, and contact lens wearers, and they performed simulated office work again during 300-minute exposures, 5-hour exposures. They performed text typing, proofreading, and addition, which we've already talked about. The exposures consisted for Group 1 of 4 levels of relative humidity, all of them taking place in clean air at 22 degrees. 5, which is very dry, 15, which is normally dry for northern regions in winter, 25 and 35% relative humidity. So if there is an effect of humidity, we're exaggerating it by going all the way down to 5. Group 2 experienced in polluted air 3 different temperatures. And the humidity was constant absolute humidity corresponding to 15% relative at 22 degrees. So fairly dry air at 22, even drier at 26, not so dry at 18. And we were interested in the effects of temperature on the same symptoms as the effects of dry air. And they also experienced a control condition of 35% relative at 22. So you will note that both groups experienced 15% and 35% at 22 degrees, so that we had the full group of 60 available for that comparison. To cut a long story short, because my lecture today is about the effects on office work, we did a lot of objective measurements, as sophisticated as we could with medical students doing them, of the effects on the eyes, skin, and nose. There were significant effects of relative humidity on the skin and eyes. They were small. They were of no clinical significance whatsoever, and there were no effects that could be discerned at all on the nose. Now, that probably doesn't tally with your experience of flying in an aircraft, where everybody knows humidity is very low because it's minus 50 outside the aircraft and the air is brought in and heated, so it becomes extremely dry in an aircraft. Most people, those who are not, who don't think it is because of the altitude and the pressure, which it isn't. That has been shown in experiments performed in a very sophisticated anaerobic chamber in Germany. They blame the low humidity. We've shown that it isn't that. In simulated aircraft environments in our laboratories, we have in a series of experiments shown conclusively that almost all of the symptoms you experience in aircraft are due to ozone reacting with skin oils and creating short-lived, very aggressive aldehydes which attack the eyes and other mucous membranes. And that is something that can be avoided. We can't remove the skin. Each of you brings in nearly 2 square meters of skin to an aircraft, but we can remove the ozone, and about half of modern aircraft do that. We hope that in the near future, all aircraft will remove the ozone before bringing it in. So, relative humidity does have an effect on the skin and eyes, but they are very small and they can be compensated. One of the ways of compensating for low humidity, and one of the reasons that the effects were small, in terms of discomfort, was that you can blink more often to re-establish the tear film. And these diagrams show you that at 5% there was a higher proportion of very short blinks. In other words, people were blinking much more often in order to re-establish their tear film. Now, that doesn't cost money. You're not even aware of it. So why should we pay a lot of money, or in the case of aircraft, lift several tons of water into the air in order to humidify the cabin, just so that you don't have to blink so often, if that's what it takes. So this is interesting. It's a mechanism, but it's a compensatory mechanism, and it means that low humidity can be compensated in terms of the eyes. We also took samples of the tear film mucus. Some of you, I'm sure, will know that the tear film consists of 3 layers. There is an aqueous layer that most people think of salt water. And on top of it, there is a very thin layer of oil, which improves the surface, the optical quality of the surface, and decreases the rate of evaporation. If you didn't have that, you would really get dry eyes. And under the aqueous layer, there is a layer of mucus, which also has to be spread thinly across the cornea. We can take samples of that and look at it in a special microscope. And here are 4 levels of what's called mucus ferning. As the mucus dries out, in a healthy and not dry eye, you see grade 1, beautiful ferning patterns. That's why it's called mucus ferning. Grade 2, the pattern starts to break up. Grade 3, there are gaps in it. And grade 4, you can't even see the ferning patterns. And you get kind of granular effect. The mucus is of poor quality. And that affects the optical quality of the eye. It even, in people with dry eye, affects their visual acuity. It's not a condition you want your eye to be in. It's uncomfortable. You can't see properly. And it is something that you would want to avoid. The mucus ferning score, taken on average over these 60 people or 30 people in group 1 case, here we see the staples showing how the mucus ferning quality was at the 4 different levels of relative humidity at 22 degrees. There was a highly statistically significant decrease in mucus ferning quality. The high score means poor quality, if you remember from the previous slide. As we passed the magic level of 20%, both conditions below 20% relative caused a decrease, a measurable decrease in mucus ferning score. Whereas 25 and 35, which many people also believe are fairly dry, and for people living in the tropics are extremely dry, they showed no difference between each other. And then in group 2, who experienced 3 different temperatures, we could produce the same increase in mucus ferning score, in other words, decrease in the quality of the eye mucus, by raising the temperature above 22 degrees. You can see there's a statistically significant difference between 22 and 26 degrees at the same absolute relative humidity of 2.4 grams per kilo of air, corresponding to 15% at 22 degrees. So the conclusion is that if we have problems with our eyes in low humidity, we should drop the temperature to compensate for that. Low relative humidity had a negative effect at 22 degrees in clean air. It was worse at 5 and 15 than at 25 and 35, as you saw in the staples. Raised temperature had a negative effect in polluted air. It was worse at 26 than at 22 or 18. Again, all of these effects were statistically significant. The practical implications of these findings are that air temperature should not be above 22 degrees if relative humidity has to be below 20. In other words, for example, in cold regions in winter and in aircraft cabins. But there's only mild discomfort and barely measurable effects on eyes and skin, and these hardly justify the expense and health risks of humidification. These have been well documented. I'm not going to go into them. If you raise the humidity in cold conditions, you get condensation in places that are hard to reach and are difficult to heat, and that can lead to mold growth and an enormous decrease in the quality of the air, even to health problems as a result of water damage. So we try to avoid humidifying in the northern part of Sweden, and we compensate by lowering the temperature indoors instead in winter and asking people to wear slightly thicker clothing to compensate for that. But in this experiment, the subjects worked at 3 tests, 3 examples of office work. We had included that only to ensure that they didn't sleep, because one of the ways people deal with the aircraft cabin environment is to shut their eyes. If they are experiencing slightly sore eyes, they can deal with that by shutting their eyes as they take a long flight across the Atlantic, for example. So we wanted them to make sure that they kept their eyes open for 5 hours. And the best way to do that was to get them to look at screens. So nobody expected low humidity to have an effect on performance. It's never been shown before. But we found apparently significant effects. I say apparently, because this is one single observation, and we have not yet got round to repeating it, and nobody else has either, as far as I know. If any of you know out there of another experiment similar to this, please let me know, because we would like to believe our own results, but we don't claim that these are other than statistically significant in this particular experiment. What we observed was that as we reduced the temperature, the humidity at 22 degrees from 35 down to 5, we saw a statistically significant decrease in typing speed. It's quite a large effect, and it is extremely significant. 5 hours of work gives you high levels of significance. On proofreading, there was also a statistically significant negative effect of low humidity. And on the number of additions performed per minute, there was a sharp decrease as we went down to the lowest level of humidity. Again, unbelievable levels of significance. So these are not chance observations. It was a well-designed experiment with balanced order of exposure. It can't be put down to some defect in the design of the experiment. We look forward to having these results confirmed in other experiments. If they are, they might justify humidification, or at least a rather drastic decrease in indoor temperatures using the mechanism that we've just documented. And that would be bad news for energy conservation, because humidifying takes a lot of energy. The possible mechanisms for a performance effect of low RH, you don't just have to show that they occur, you have to give some idea as to why they could occur. We have 3 theories as to why they might occur. The first, we don't think is very likely. Discomfort distracts attention. Well, there was very little discomfort. We were following how much discomfort there was, and it was low because they were able to increase the blink rate. But this compensatory mechanism of increased blinking may reduce the visual data acquisition rate. In other words, your attention is on hold during each blink. You're not aware of it, but it's logically so that when your eyelids are down, you can't see anything. So your rate of acquiring data is on hold during each blink. The brain is so well constructed that it maintains your vision. So you think you're seeing things continuously, but you're not. You can miss things that happen. And particularly on a computer, where things are changing all the time, you may miss something and have to go back if you happen to blink at the critical moment when the screen changed. So we think that it may simply be that low humidity causes increased blinking. We've documented that. And you therefore have to work more slowly in order to acquire and process the same amount of information per minute. There is another possibility, and that is that we know that tear film deterioration reduces visual acuity, and it may take slightly longer to focus on the screen when you have drier eyes, as we know it does with patients with dry eye syndrome, where they have clinically dry eyes because they're not producing enough tear film or they're producing a poor quality of mucus. So we come back to the conclusion screen. I've now placed bullet point 2 in bold. Raised temperatures reduce relative humidity, and below 20%, this affects the eyes enough to reduce work rate. That's what we can conclude from Research Project 1160, which you can obtain from ASHRAE and read for yourself, or read in our shortened version of the final report in HVAC&R Research Journal. I'm now going to go over to experiments on temperature. And exceptionally, I'm going to show you an experiment that I did not perform. At the time this experiment was performed by Pepler and Warner, I was doing experiments here in Sweden on children, which I mentioned, at least, I've done many more since, but to which I mentioned in my previous webinar. That was done in 1967 and reported in 1967. Pepper and Warner reported their results in 1968, and it was first then that I became aware of their experiment. It was an early climate chamber experiment on office work, and it covered the range 17 to 33. That's most unusual, because from a practical point of view, we know people won't put up with 17-degree or 33-degree temperatures in offices nowadays. We're used to a higher level of thermal control. But Pepper and Warner got 72 subjects, equal numbers of male and female, divided them into 6 groups, and had them work through a textbook week after week, which contained a question and answer, a series of question and answers after each section. So they were able to see how quickly they worked and how many errors they made in answering the question. It was done with paper and pencil because we didn't have computers in 1968. Some of you probably weren't even around at that time, but all of our experiments were done with paper and pencil at that time. 6 temperature conditions were experienced in balanced order, 3-hour exposures. Each exposure took place at the same day and time of day each week for 6 weeks. So each subject experienced all 6 conditions. And they dealt with the parallel testing versions problem by using the same chapter for all groups in a given week. Okay, so they confounded chapter with week. And if there was a difference between chapters, it would be confounded with differences between weeks, which corresponds to learning, if you like, how to deal with this experimental situation. All conditions occurred in every week, so that if there was anything special about a given week, heavy snowfall, for example, then it would affect all conditions equally. The subjects wore standard cotton twill clothing. They calculated it as 0.52 kilo. In the internationally accepted insulation value for clothing. They wore woolen socks but no shoes, long trousers and a long-sleeved shirt, so they were covered up. They didn't have very much bare skin. The humidity was 45%, which we would regard, after looking at my previous experiment, as neither humid nor dry. Air velocity, 0.15 meter per second, in other words, no drafts. They weren't standing in a blast of air from an air conditioning unit. And the temperatures, as I said, ranged from nearly about 17 to about 33. They were in degrees Fahrenheit. The lowest was 62 and the highest was 92 degrees Fahrenheit, for those of you who still think in those terms. Pepper and Warner's conclusions, reported in that paper, were that percentage errors were unaffected by conditions. In that, we agree. That's what we find too. People work at a rate that maintains their normal error level. There were significant effects on the time taken to complete a chapter, and there were significant effects on reported effort. All good stuff. But the authors reported least effort and best performance at 27 degrees, and this is apparently still quoted by some people as the result of that experiment. 40 years ago, I wrote to the editor of that journal and I corrected that impression in several of my papers. Best performance, as defined by Pepper and Warner, was fewest errors per hour. And that's a very curious way of measuring performance, because the reason that they made fewer errors at 27 degrees was because they were working slowly at that temperature. This is the time it took them to complete a unit of a chapter in units of 3 minutes. And you can see that the subjects worked best. This is an average of all 72 subjects. They worked best at 20 degrees. They worked more quickly. They took less time. They worked most slowly at around 27, 26.7, I think it is, the actual value. And there was a reversal of the effect as sweating was established above 27 degrees, because it doesn't feel so hot once sweating is able to take place. So even unfit people will begin to sweat above 27 degrees. if they had been fit, they would have, or if they had been living in the tropics, they would have been able to begin sweating around 20 degrees, and there would have been very little effect of temperature in this range. You can see a slight indication that it's not very nice to work in 17 degrees either, an uptick at that end in the time taken to complete. These were significant differences, even according to the original authors. This graph shows how many percent of time they lost under each of these conditions. Just to show you that at 27 degrees, they were losing 8% of their productivity. They were working 8% more slowly at 27 degrees in comparison with 20. I've normalized the results to show one at 20 degrees. Another aspect not reported by the authors was that women worked much faster than men throughout, at all conditions, but there were similar trends in both genders. It wasn't very common to acknowledge that women sometimes are better than men at some things. And in fact, in my experiments, at many things. For example, in my experiments in South Africa, women were consistently better than men at manual dexterity tasks. Least effort was exerted at 27 degrees. This is on a scale of effort. So these are completely arbitrary units, but moderate effort was 4 and slight effort at 3. And you can see that least effort was exerted at 27, and more effort had to be exerted both above and below that thermal condition. And this was the same for both men and women. In other words, as it gets difficult to work because it's hot, you put in more effort. But within the thermally comfortable range, you exert less effort anyway, for no particular reason. You think, perhaps, that you're working as well. You report less effort, but that's because you're working more slowly, so you didn't have to put in so much effort to maintain that lower work rate. They also asked them about their thermal comfort, and they were incredibly tolerant. In those days, we didn't have such good thermal control in buildings. And you can see that their neutral temperature with that very light clothing, half a clo, was 25 degrees. They reported on average that 22 degrees was slightly cool, and that 18.8 degrees, 19 degrees was cool. You wouldn't get many people nowadays to work in 19 degrees, sitting still for that many hours. Slightly warm at 28. Again, today, most people would say it's hot at 28 degrees, people in this part of the world anyway, and warm at 31 degrees. A very tolerant subjective response to temperature. It looks like this graphically. It's the same data that I've shown there. I was just averaging. You can see a very small tendency for women to consider it hotter than men do at the top end and colder than men consider it at the lower end. But it's absolutely negligible difference when they are in standard clothing. Normally we find that's the case. The difference between the systematic difference there is in practice between men and women is that women have clothing in which the insulation is less effectively distributed over the body area. They show more skin. They have legs that are bare, arms that are often bare when men don't. And so they are more sensitive to cold and heat. And in this case, they weren't. They considered 20 degrees cool. 25 was a neutral temperature. If we go to comparing now with present-day norms for temperature, ASHRAE would tell us, using the adaptive thermal comfort model, that it's 80% will be comfortable in the range of 18.5 to 25 degrees. Now, anyone running a building knows that that's not entirely true. You will get some very, very determined opposition to running an office at 18.5 degrees and also to running it at 25. But that's the norm today. It's supposed to be okay, 80% comfortable in that range. And the European corresponding norm is from 19.5 to 26.5. Now, these ranges are, in my view, biased in order to save energy. People don't actually want to work within, at the edges of these ranges. Notice that in this experiment carried out in 1968, even with people who were extremely tolerant of temperature changes, Neutral temperature was at the upper end of these ranges, and optimal performance occurred at the lower limit. Performance decreased by 8% within this 80% comfort range, and that tallies with many other experiments we have done. Thermal comfort is no guarantee for performance. Just because 80% accept it, it doesn't mean they're all working as well. They maintain thermal comfort by working more slowly, reducing their metabolic rate. That leads to a reduction in effort and a reduction in performance. Having looked at Pepper and Warner's excellent experiment, I'm going to go on to some of DTU's experiments, which were carried out by colleagues, Balasova and Clausen, and in which I had a part. We performed an experiment to show how multiple indoor environmental quality factors affect office work. This was shown in a conference paper to Klima 2007. We took 56 subjects, nearly equal numbers of men and women, 24-year-old. They performed office work, addition, for 3 hours. Really boring, quite hard work. They did 15 minutes work in each of 8 stated conditions. And all 8 conditions commonly occur in offices. The conditions were the combinations, 2 by 2 by 2, of 2 temperatures, 2 office background noise levels, and 2 air pollution levels. The temperature was either 23.5, not cold, but not warm either, or 28, quite warm, but not hot. The office background noise was either just background noise or it was recorded office noise, which made it seem as if you were in an open office with a lot of people present and machines working, telephones ringing and so on. Quite distracting office background noise, or a private office. And the air pollution was either with a source absent or present behind a screen, the carpet that we've used in previous experiments. The work rate under the 4 conditions that are shown here was significantly decreased by multiple factors. The reference was cool, quiet, and clean, 23.5, private office, and no pollution source present other than themselves. That is the left-hand condition. When we made it warm and noisy, in other words, 28 degrees and other people present behind the screen, recorded noise, we got a significant decrease in work rate. When we made it warm and polluted, that is 28 degrees and the carpet present as a source of pollution, we got a slight decrease too, also statistically significant. And when all 3 factors were present, warm, noisy, and polluted, we got a highly significant decrease in performance, even on a 15-minute exposure to each one. Now, that is, we didn't expect to get statistically significant results. We were more interested in the subjective results. But it's very gratifying that even in such short exposures, we can show that indoor environmental quality has such a systematic effect. These are not additive effects. We're not getting a decrease that is double, but they are additive. But they are not exactly quantitatively additive. Measured work rate decreased by up to 8%. You're starting to recognize that magnitude from our other experiments. Each indoor environmental quality factor had some negative effect, but the combined effects were less than strictly additive. Self-estimated performance was much more affected than measured performance. We'll show you that in a minute. Every single factor decreased self-estimated performance. In other words, they thought they were working less well even when they weren't. We can also draw the conclusion that cool, quiet, and clean offices will pay for themselves. 8% is a lot of money, and if you work that out in terms of the wage bill. Now expressed as a percentage decrease in work rate, the same 4 conditions, warm, noisy, warm, polluted, and warm, noisy, polluted, we can see an 8% decrease in work rate. If we look at self-estimated performance, it's decreased significantly under each of those conditions, and it's a much bigger decrease. It goes from 80% of maximum down to below 60 in some cases. That's a much more than an 8% decrease. So you can't rely on self-estimated performance to give you a quantitative estimate of how much more slowly people are working. Under the same 4 conditions, the percentage decrease was between 20 and 30%, as you can see here. This is going from cool, quiet, clean to warm, noisy, warm, polluted, and warm, noisy, polluted. In this case, warm, noisy was seen as worse than warm, polluted, but it wasn't. They were about the same in terms of actual decrease of performance. But it's more or less parallels the effects of that we could measure objectively in terms of the amount of work they did. Now, I want to show you warm by itself and noisy by itself. These were not significant by themselves, but warm, noisy was, of course, as you've seen. But they at least occur systematically where you'd expect them to occur, in between cool, quiet, clean and warm, noisy. But again, I emphasize these were not significantly worse than cool, quiet and clean when they occurred separately. And the remaining 2 conditions, polluted and warm, polluted, again occurred in between what you'd expect, the cool, quiet, clean condition, and the warm, noisy, polluted condition that we know differ significantly. They were in between. But again, neither of those conditions on their own produced a significant decrease in performance. But I just want to show you that self-estimated performance did decrease, and that was a significant decrease. Now, I want to show you a final experiment rather quickly, because we've gone over time. Self-selected improvements in indoor environmental quality. Again, my colleague Georg Clausen was the experimenter, and I had a part in it. We allowed subjects to choose what improvements they wanted in noise, lighting, view out, privacy, temperature, indoor air quality. And the conditions were to either have a 50% budget for improvements, which they either did or did not choose, or to experience none of the improvements or 100% of the budget. In other words, all of the improvements. Usual versus improved indoor environmental quality. Each of these 6 IEQ factors took 2 levels. 55 dBA traffic noise versus 45, in other words, better insulating windows. Glare and flicker versus designer lighting, really good lighting. View out versus working in a cubicle. A private office versus the noise of an open plan office, recorded of course. 27 versus 22. And stuffy air versus clean air. In other words, the pollution source present behind a screen or not. And the relative costs of the improvements were estimated by consultants, and we then allowed one group to choose. 99 subjects were randomized to 4 conditions, so there were 4 groups. One group worked with 0 budget, no improvements. Another group at the bottom worked with all of the improvements. In between, we had a group who had been allowed to choose which improvements they could afford. So they were personalized improvements. Somebody sensitive to noise would choose to reduce the noise level. Somebody who can't stand working in a cubicle would choose the view out, and so on. And then we randomized another group in pairs to experience exactly the same conditions as had been chosen by the other group. So there's enormous variance because they all chose different things. And so we can compare the same conditions that have been either chosen or not chosen by the individual concerned. They worked for 2 hours under one condition only. The results, one is that all possible combinations were chosen. There was no agreement at all on what was important. Now that should make architects think. We rely on architects and indoor environmental designers to tell us what's important. And they don't know because it's different for each individual. So we are randomizing people into improvements that we have paid for, even though we don't know that they're the ones they think are important. That's the first conclusion. And that was what we were after. Do they all choose the same improvements after having experienced every one of them? Self-estimated performance and subjective acceptability improved with budget level. As they made successively 50% or 100% improvements, we got improved self-estimated performance and subjective acceptability. In this experiment, because of the enormous variability between the conditions and between individuals, we could not show measured performance was affected. There were too many variables in too small groups, but the trend was the same. So if we make an index of performance based on all the work they did, you can see, compared to the worst condition, zero budget, the 100% budget resulted in about a 7% faster working. In between, we have the 50% budget conditions, and the ones who chose the conditions worked faster than the ones who had not been able to choose. They'd just been randomized to sit beside somebody else who'd chosen that set of conditions. Okay? So that's what we expect, but I emphasize it's not a statistically significant difference. What we could show was a difference in subjective response. There was a trend to improving IQ to improve performance. Self-selected improvements worked better than non-selected improvements, and the magnitude of the effect was up to 8%. Self-estimated performance after 70 minutes was significantly different between the conditions. As you can see, there's a trend for increased budget to give increased self-estimated performance. As you can see, again, as in the measured work, the self-selected 50% budget came out above the random budget, but that was not as statistically significant in this after 70 minutes. But after 114 minutes, it was. Improving indoor environmental quality improved self-estimated performance significantly after 70 minutes and after 114 minutes. At the 50% budget level, choice tended to improve self-estimated performance, but that wasn't significant. After 114 minutes, self-estimated performance at the 50% budget level with choice was almost as high as it was with a 100% budget in this diagram. So spending half as much but letting people choose resulted in their estimate that they worked just as well as if they'd had all of the improvements. So there's a possibility for improving there if you allow people to choose which improvements they get. The percent dissatisfied with the IQ was statistically different between choice and no choice. Improving IQ significantly and linearly decreased the percent dissatisfied. That's a P less than 0.01 effect. And critically, at the 50% budget level, allowing individual choice significantly decreased the percent dissatisfied, P less than 0.02. And this was a big effect. It was as much as 28%. Allowing individual choice at the 50% budget level did in fact result in fewer dissatisfied than at the 100% budget level. This is that critical diagram where the decrease due to having no choice was statistically significant. So this tallies with what we measured in terms of their performance, in what they said in terms of their self-estimated performance, but in terms of how dissatisfied they were, it was actually a significant difference. We want to go on with this kind of experimental architecture, experimental environmental design, but as far as I know, nobody has done such an experiment since then. So now we have all of our conclusions in bold. The final bullet point is that office work is performed more slowly towards the warm end of the adaptive thermal comfort range. I'm not going to give you these multiple factors as a firm conclusion yet, but I wanted to show you them in the course of this lecture. Thank you very much. We'll take questions now. If any of you have written some in, Veronica will have them with her, and I will attempt to answer them to the best of my ability.
Well, unfortunately, Professor Wyon, we don't have any questions from the online audience, but we have a couple of people in the audience here in Sweden, in Stockholm. Do you have any questions? I have one.
Hi, my name is Joachim Ernback. I work for a company called Plantagon. I would like to know if you ever tried to introduce plants into the environment and seen the effect of plants' ability to improve the air quality.
I know of some such experiments, but we ourselves haven't done any. The problem is that you need an enormous leaf area in order to produce a measurable change in the air quality, whether or not it affects people. And the other problem is that plants need soil. And soil in itself, because it's wet, is a place where mold can grow. And it can the net result can be a decrease in the air quality due to that. If you could use hydroponics, that is, growing plants without soil, I think you would have a chance. But again, you would have to be in an office that looked more like a jungle than what we know as an office before it had a measurable effect on the air pollutants. But I'm willing to believe that there is an effect, but I know of no such reliable experiment that has shown such an effect.
Well, I think it's quite fascinating that just giving people a choice from some indoor environmental quality measures and just what you prefer, you can cope with the bad things. You can even cope with quite a bad environment if you just choose whatever you prefer.
Right. In the 50% budget condition, they still had quite a few of the 6 negative factors in the environment because they couldn't afford all of them. Sometimes they could only afford 2 because some of the improvements, like getting a private office, are very expensive.
So it should be quite easy to keep people happy, but it's not sure that they are healthy.
Well, I think that within this level where none of these conditions are dangerous to health, except for people who are allergic to some pollutant in the air. With that exception, which is well documented clinically, I think we can say that all of these conditions are no danger to health, except that working under stress, the stress of trying to cope with suboptimal working conditions can have a long-term negative effect on health.
Thank you, Professor Wyon. And for those of you online, if you want to listen to Professor Wyon in Swedish, we have a lecture at 11:30, a webinar then. Otherwise, I thank you all for watching and thank you for today.
Thank you.